Okay, good morning, everyone. So today we are going to talk about a new topic, nonlinear equations. So nonlinear equation is, you try to solve the equation fx equals 0 and f is nonlinear. So we will study maybe a few methods. So the first method, I think I have to move the screen a bit. Sorry about the screen. Yeah. Okay, so the problem is like this. So suppose you want to find a 0 of a nonlinear function f. Yeah. So you find x, so that f of x equals 0. Or suppose you have a capital function f. So this is a vector value function. Okay, so take a vector x in Rn, and then it maps to another vectors in Rn. And you want to find a vector x so that capital F of x equals 0. So where do we see those problems? Okay, so this is a problem that, a few hundred years ago, Kepler, I think Kepler, he's an Austrian astronomer. And when he observed the stars, yeah, then he see that, the star moving according to ellipsoid orbit. Yeah, so ellipse orbits, and it has some parameters A and B. Okay, and then B is like the mean anomaly, and then he need to find X, and X is a centric anomaly. Yeah. And then he found out that he had to solve this system, and this equation. And you can see that this equation is non-linear. I mean, it's not like a quadratic formula that you can have a simple formula. But this one, you have x here and you have sine of x here. So there is no way for you to find the solution easily. Okay. And now another equation is, okay, so this one is only one equation. Yeah. But here you have a system of 3 equations, and it's non-linear. You see that you have a x times y, and you have a y squared here. You have e to the x here, and you have to solve to get x, y, and z. Okay. And another equation that, what we call a navigation equation. So this one is come up in a GPS system. So what is a GPS? Is a global position system, right? So suppose I click on this one. So can you see my screen now? Okay, so you can see my screen, yeah? So anyway, so now I think because of a copyright problem, I think I cannot play the whole video, but I will post a link into the slide. And what happened is in the navigation equations, you have 4 satellites, yeah. Okay, and well, maybe let me try to draw pictures. Yeah, so it's better to draw pictures. Then I will go back to this. So suppose you want to find out your location, right? So you turn on your Google Maps, okay, and then you turn on location, you turn on GPS, and then it just gives you the location exactly. But how does it work? Okay, so it works based on GPS, the global satellite system. Sorry, global positional system. Yeah, GPS. So what it works is like this. So your mobile phone is. So suppose your mobile phone is here. Okay, so you're holding your mobile phone. So an iPhone 3, 4, 5, whatever. Then actually it's receiving the signals from 4 satellites in the sky. Okay, so we have a constellation of, I believe that maybe 72 satellites or something. But you need only 4 satellites for it to work. Okay, so what each satellite gives the signals to your phone. So it gives, you know, the position of the satellite. Yeah. So say X1, Y1, Z1. Yeah. And further than that, it gives the timestamp. Yeah. So when it sends you a signal, suppose send your signals at 10 o'clock. Okay. And then so it send it to you, right? So then another satellite give you X2, Y2, Z2, T2. Okay, so it gives you your information and so on. So you have 4 signals from 4 satellites, yeah. And each signal is just a collection of 4 numbers, the X and Y, Z coordinates, and the time send you the signals. Okay, so they are given. So now, what is your position? Well, your position is something unknown, right? So you have X, Y, Z is your location, is unknown, right? And then you have a delay, you know, like when, what is a delay? It's like when you receive signals, yeah? So let's send you at 10 o'clock, you receive at 10:05, for example. So it took 5 seconds to travel from the satellites to your phone. But then there's a delay that, you know, depends on your iPhone as well. So it's unique. And so it's unknown. So you have 4 unknowns. Okay. So now how do we find those 4 unknowns? And see, when you have the coordinates, then you just look up the maps, and then it gives you a position of your phone on the maps, yeah, and your phone will be your location. So what is the equation? Well, so now what is the distance from here to here? So what is the distance from the first satellite to you? The distance can be computed by x1 minus x plus y1 minus y plus z1 minus z square. Okay, so this is a distance. So the whole thing, take the square root, yeah. So this one gives you the distance, yeah. So I'll combine the square root, go down here. And secondly, you know, you have the second distance, you know, like x2 minus x squared plus y2 minus y squared plus z2 minus z squared. Okay, so you have second distance, yeah. However, so now suppose now I just take the first distance, yeah. So the first distance is x1 minus x squared plus y1 minus y squared plus z1 minus z squared, right? So this is a distance, yeah. However, you know, remember, if you remember your physics in first year, the distance is just the speed multiplied by the time. Okay, so So the speed multiplied by the time is the speed of the electromagnetic wave, right? Because I mean everything is just radio wave, so sent from the satellite to your phone. So what is the speed of the wave? So what is the speed of the wave? So how fast the radio wave can travel? Anyone remember your physics? How fast, you know, I mean, electromagnetic wave travels? Nobody took physics? Nobody took first year physics, or you've read it somewhere, or yeah, but at least you've read it somewhere, right? I mean, you should know how fast your suppose you say something to your mobile phone, right? Then you should know like how fast the signals travel from your mobile phone to say the next mobile phone. No? Anyway, so I just tell you that the speed of the wave is c, yeah, which is the speed of light, yeah. So this one is the speed of light. So what is the speed of light? It's very fast, yeah, about 300,000 kilometers per second, yeah. And so if you know a bit about more physics, then nothing can travel faster than speed of light, yeah. I mean, nothing in this universe can travel faster than light. Okay, so then then this is the speed multiplied by the time. Okay, so remember you receive, so this one is the time you receive the signals from the satellite, yeah. So then the time you receive the signal, okay. So this one is the time you receive the signals. Receive time, receive the signal, yeah. And minus, well, minus the time the signals were sent, yeah. So T1. Okay, so and then there is some delay, so some bias. So this one is a delay from your device, yeah. You know, I mean there is some delay from your phone that cause some tiny delay. So you have, so how many equations you have? So you have 4 satellites, right? Remember? So how many equations you have? So you have x1, y1, z1, and here you have t1, right? Okay, and then you do the second satellite, yeah. Then you got x2 minus x squared plus y2 minus y squared plus z2 minus z squared equals c, yeah, plus b minus d2, right? So how many equations totally? How many equations? 4. We have 4 satellites, remember? You know, remember we have 4 satellites, yeah. Okay, 4 satellites, yeah. So why we need 4 satellites? Well, because how many is unknown? Well, you have 4 unknowns, yeah. So you receive the signal, so you know the time you receive the signal. You have a clock, but you have the bias, so the bias is unknown. So you have 4 equations, 4 unknowns, yeah. So that is the what they call a navigation equation. So that is the equation behind your mobile phone trying to find your location on the map, right? So you see, so this one is the slide that gives you the equation. So the distance, yeah, the distance between you and the satellites, yeah, is, well, I just squared, yeah, is the same as the time taken by the signals to travel from the satellite to you. So you have, so essentially you need only 4 satellites because you have 4 unknowns. If you have more, then it's better, but essentially you need only four satellites. Yeah. So then you have a system of 4 nonlinear equations and you need to solve it, right? So now that is the motivation for you to solve the system of nonlinear equations. So now we just go back to the single equation, yeah, just function of one variables. So the bisection method, is the simplest method you can have. So bisection method works like this. So suppose you have a function. Suppose you have a continuous function like this, yeah. And maybe, you know, your function just have the 0 right here, right? Then first I just check, suppose I have an interval. So this one is like A and this one is B. Yeah. Then first I just check f of A and f of B. Okay. Then if it's less than 0, yeah, then I know that it has, f has a 0 in AB, right? In the intervals AB, yeah. And now what is the next step? So the next step is I try to find the midpoint. Now the midpoint will be, say, x0 is A plus B over 2. Okay, so the midpoint will be right here. So this one will be my x0. Okay. And now I'm checking. Okay, so now I'm checking if f a time fx0 is less than 0. Okay, or f x0 time fb less than 0. Okay, so now you can see that in this case, this one is not correct, right? So this one is not correct. So fx0 and fb now is the same signs. Yeah, it's positive. Okay, so this one is we check, yeah. And if f of a time fx0 is less than 0, then you define a new interval. So now you define a new intervals. So define a to be a, right? So a is the same as the point before, but now your new b will be x0, right? And then you repeat the whole process. Okay, so that is the bisection method. So repeat the process. Yeah. So you see that, you know, I mean, for the next step, you have fa and f of x0 is different sign. Yeah. Then you try to find the middle point. So the middle point now maybe somewhere very close here, right? And then you do the same process, that just keep squeezing, you know, until you get to this 0. Okay. So, but what is the assumption here? So why can we do this? So what is the assumption? So what is the assumption? Yes, correct. F has to be continuous. Okay, so this, the whole step here, this key step, okay, is what we call the intermediate value theorem. So intermediate value theorem. And this only works if f is continuous. Okay, so f is continuous. Otherwise, it's not correct, right? Because you can draw pictures. You can draw pictures like, suppose I have f is like this. You know, there's a big jump here. And so you see, if you take A to be here, B to be here, then FA and FB, you know, opposite signs, but there's no zeros in between because F is not continuous. Okay, so this method, you have to make sure that the function is continuous. Otherwise, it's not going to work. Okay, so that is the key thing. So now if you write down in terms of the algorithm, then it looks like this. So step 1, you find the intervals. So that FA and FB, you know, I mean, I can start with FAN, start with IN and BN, yeah. So the FAN and FBN have opposite signs, yeah. And then you find the midpoint of the intervals. Okay, so this is exactly what we did in the pictures, yeah. And then now you define the new intervals, yeah. So you define the new intervals. If you know the right intervals, sorry, if the left intervals, the two ends have opposite signs, then you define that new intervals, you know, to be the new IN plus 1, BN plus 1. Or, you know, I mean, if you choose the right intervals, if they have opposite signs, yeah, if XN and BN have opposite signs, and you choose this one to be your new interval, IN plus 1, BN plus 1. Or if, you know, if you check xn equals 0, then you stop. That is your 0 already. Okay. And, you know, I mean, you just repeat. So you repeat means that you go back to step 2, right? And you find a midpoint and again. Yeah. So why does the bisection method works? Yeah. So you answered already, because f is continuous. So we can use the intermediate value theorem. And what is the conversion rate? Well, so what is a conversion rate? So the conversion rate is, you know, you see that so you see that every step, yeah. So if you so the conversion rate is so you remember we have say A0, B0 is the initial interval, right? Yeah. So this one is FA0 times FB0 is opposite sign, yeah. And then you have A1, B1. Okay, so this one could be the left or the right, but I mean, I just know that B1 minus A1, the distance will be 1/2 of the original intervals. Yeah. So it could be the half part or the right, sorry, the left half or the right half of the original intervals. But the effect is to reduce the width by 1/2. And then you have B2 minus A2 is 1/2 of B1 minus A1. And so this one is 1/4 of B0 minus A0, right? And so on. So in general, you have Bn minus An, which is 1/2 to the n B0 minus A0. So you see this one go to 0 when n go to infinity, right? So Bn minus An will go to 0, and it squeeze down the 0 in between, right? So the 0 will be inside the intervals A and Bn, and the conversion will be 1/2 to the n. So that is the conversion rate. Yeah. Okay. And you see that it's not very fast, right? Because if you remember like 1/10, so like 1/2 raised to the n, it's still like 10 to the minus 3, roughly. So it will go to 0, but not very fast, okay? And we can implement it in MATLAB. So suppose I have a function, yeah, x minus cosine x equals 0. Then you can write a MATLAB script like this. So first, you define the left points of the intervals a equals 0, the right hand side equals 2, and you can define f as an anonymous function, right? And now, because you don't know how many times you do the iteration, so maybe we just use a while loop, okay? And now we compute the midpoint. So the midpoint will be xn is just 1/2 of a plus b, yeah? And then now I check whether xn is the solution, yeah? So if f, you see, I mean, for MATLAB, everything less than epsilon can be considered to be 0. So we just check f of xn is less than epsilon, yeah? So remember, epsilon is about 2.2 10 to the minus 16, yeah? And then you raise the flag, okay? Because the flag here initially just equals 0. So if it's still equals 0, you skip doing this. And if you find a 0, you raise the flag and you stop, okay? Otherwise, you check, okay? So if the left intervals, okay, the FA, FXA in opposite sides, then you modify your B. Okay, so now A is the same as A, but B is just the midpoint. Otherwise, then you choose your, you move the right, sorry, you choose the right half, okay? So by this command, and then you just repeat, yeah? And so we can run this, yeah? So now suppose I run this, so let me run this for you. Let me move to the correct directory first before I share my screen. So we going to see how it works. So now let me share my screen, my MATLAB screen. And okay, so you can see that, so this is exactly the script, yeah. So we have f is defined here, and then xn is the midpoint here, and then you just run it. You hit the button and you run it. And you see, so 0 of f is 0.73 something. So you can check that. So f of xn is 0, you see? So, and say this one, x equal cosine x, is you cannot solve it by a formula. It's not easy, right? Okay, so now that is the bisection method. So any question? So far so good, right? Okay, so now the next one is, okay, so we talk about the convergent of bisection method. So the first, the intermediate value theorem say that there exists a solution, yeah, or assume that a function continuous. And then the width of the interval just go down at 1/2 to the n, yeah. And then because 1/2 to the n go to 0 a bit slow. So you see that it's a bit slow to go to the solution, but at least you can find the solution. Okay, so now the next method is fixed point iteration. Yeah. So fixed point iteration is like this. So suppose I want to solve this nonlinear equation x equal e to the minus x. Okay. Now I will start at some point, say x0. So x0 equals 0.5. Then I just put x1 to be e to the minus x0. And x2 is e to the minus x1 and so on. Yeah. So you can see it like, okay, so suppose I make like a slide show, and so let's see whether you can see this. Yeah. So see, initially we start at 0.5, right? Yeah. Then we we evaluate the function at 0.5. So you got this point. Yeah. And then you take reflection over the line y equal x, and you got x2. And well, maybe this one you see the whole sequence. You see, so it's like a spiral, right? So it's going spiral. So just going to the intersection. Yeah. Okay, so this is the point right here. Okay, so now you can write down a MATLAB script for that algorithm. So you see, you can reuse a variable, so you don't have to use x1 equal e to the minus x0, but you just put in x. So x equal e to the minus x, and so on. Yeah. And then you see that eventually it's going to converge. Yeah. So the equation, sorry, the general form is you just have x equal g of x, right? And then you have an initial guess, and then you just define xn plus 1 equal g to the xn, and so on. Yeah. So then x star is a solution, okay, of gx star equal x star. Then we call it x star as a fixed point. So now remember before, right? Before we have e to x e to the minus x. Yeah. So now what happened if I replace the equation by x equal e to the x? Okay, so what happened? So now, I mean, can you try it and let me know what happened, because I want to have a small quiz. So this one is in the, if you go to Moodle and you go to interactive documents, okay, then you see that we have a fixed point iteration. So let me share you the screen here. So if you go to fixed point iteration, yeah, so you see this is the, yeah, so this is the quiz here. Yeah. So now suppose I try to solve x equal e to the x, okay, with a fixed point x equals 0.5, x0 equals 0.5. So what is going to happen? Does it converge to the solution or blows up? Okay, so somebody said that it blows up. Yeah. So you've tried already. So anyone said that it converges to the solution? So you've tried already, right? So So now I can try it. Yeah. So now suppose I try it. I go back to my MATLAB and I use this one. So fixed point, my fixed point. Okay. So this is the script for fixed point. And now, so remember, if I put e to the minus x here, I run it. Then see after 15 iteration, then you see that it stay at the 0.56. Yeah. But now I put, instead of minus x, I put plus x and I run it. You see, it blows up. So after 4 iteration, okay, it blows up to infinity. You see, so this method is not always converge, you know. I mean, you see that you change the sign only plus to minus. And it just, I mean, from minus to plus, sorry, it just blows up. Okay. So what is going on here? So we need to study the theory a bit, yeah. So now if I go back to the theory, then so what is the theory? So the theory is now in order to see what is going on, we need to define what is the errors, yeah. So the errors is just the difference between your approximation, your xn minus x star is the true solution, yeah. So remember, x star is the point that x star equal g of x star, right? And then now, if I compute en plus 1, yeah, so this is the error at the next iteration, then it will be xn plus 1 minus x star, right? But remember how we define xn plus 1. So xn plus 1 is just g of xn, right? So this is your fixed point iteration. And what is x star? So x star is a solution of x star equal g of x star. So I just replace, you know, this xn plus 1 by g of xn and x star by g of x star, right? And then what is xn? So xn is just en plus x star, right? So this one is just a simple substitution. Then if you remember Taylor expansion, yeah, then the Taylor expansion of the function g around the point x star, okay, will be of this form, yeah. So remember Taylor expansion, yeah. And then this so maybe let me write down Taylor expansion, yeah. So if you don't remember Taylor expansion, then we need to review Taylor expansion, because so remember, what is a Taylor expansion? So anyone give me the Taylor expansion formula? You can look it up. Google. So what is the Taylor expansion formula? The one that you are familiar with? Anyone type in the chat box? What is the Taylor expansion formula? So what is the Taylor expansion formula that you know of? Or you just look it up? Anyone? You still there? Are you drinking coffee or? So what is the Taylor formula that you know of? Just look it up. I mean, you have your laptop with you, right? You can look it up on Google. What is the Taylor formula? Or you can just talk, talk to Siri. What is the Taylor formula? Okay, so this is the one that you know, right? So fx equal fx0 plus f prime. Well, you should have f prime and x0, right? X minus x0 plus f double prime x0 2 factorial x minus x0 square and so on, right? So on. So I don't worry about the extra term, right? Yeah. And now what I want is I just put my x0 to be x star. Okay. Sorry. Now two things. First, I put f to be g. Yeah, because I'm interested in the function g. So then I have g of x, yeah, equal g of x0. Sorry, g of x0, yeah, plus g prime x0 x minus x0 plus g double prime x0 over 2 x minus x0 square, right? So plus dot dot dot. So I'm just worried about up to the second derivative, right? And now what I want is I want to put x0 to be x star, right? Remember my x star. So x star is the point that gx star equal x star. So this is the definition of x star, right? Yeah. Then I have g of x equal g of x star plus g prime of x star, right? X minus x star, right? Yeah, so far so good, right? G double prime gx star over 2 x minus x star square. Okay, so plus dot 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 dot, so I don't have to worry. Yeah. And now I do one more step. So now I will put my x. So this is x0, right? And now I will put my x to be x star plus en. Okay, so now I put x is x star plus en. So what do I have here? So on the left, I have g of x star plus en, right? Okay. And on the right, I have gx star plus g prime x star. Okay. And now what is x minus x star? Well, x minus x star is just en, right? By this relation. So it's just en. Yeah. And then the second one is just g prime x star divided by 2en squared. Okay. Dot, 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 dot. So that's exactly what I have in the slide. So now you got it, right? And now one more thing? What is this one? What is g of x star plus en? So what is x star plus en? So remember, so now if you remember en plus 1, yeah? So maybe one more thing, yeah? So let me do g of, so I just move this one to the left, yeah? So I just have gx star plus en minus gx star, okay, equal g prime x star en plus g double prime x star over 2 en square, right? Yeah. Okay, so now, so remember what is this one? What is gx star? So remember x star is just a fixed point of g, right? So if you remember, gx star is defined here, gx star equal x star. Okay, so therefore, yeah, so I have this one is x star, right? And what is this one? So what is xn plus en? Sorry, what is x star plus en? It equal x in this case, yeah, but actually it's before we say that this one is what? So remember we define what is en. So this one is x is just a dummy variable, right? Yeah. But before we had a definition of en. Okay, so en. Remember en is xn minus x star, right? Yeah. Remember, so this one is before we define xn minus x star is this error, right? So then x star plus en, right? It just equal xn. So this is a gxn, yeah. Okay. But gxn is actually, so this one is the same here, right? So what is gxn? So gxn is just xn plus 1, right? By the formula, right? So equal g prime x star en plus g prime x star over 2 en squared, right? And now this one is nothing but en plus 1. So g prime x star en plus next term en squared. Okay, so now I want you to pay attention to the last equation. So what does it mean here? So you get it, right? So now this is the one I have in the slide. So now if I go back to the slide, this is exactly what is in the slide. So you see that, you know, like by applying Taylor expansion, yeah, then you have en plus 1 is just equal g prime x star en plus some higher order terms, yeah. And now if we ignore the second order term, then en plus 1 is just equal g prime x star at en. Okay. So now we want en plus 1, or we want en in general go down to 0, right? Because the errors go down to 0, then the method converges. Okay. Then what do we expect? I mean, how do we guarantee that it's going to converge? So now I'm going to write down the last equation, yeah. So I'm going to write down the very last one. So I just have en plus 1 equal, well, approximately g prime x star at en, right? And so now you can have E1 equal G prime X star E0, right? And then E2 equal G prime X star E1, right? What is G prime X star square E0, right? And then E3 is just G prime X star E2, yeah? What is G prime X star with E0, right? And so on. So you can have En, it's just roughly equal G prime X star raised to the power N E0, right? Power N. So E0 is a fixed number, right? E0 is a fixed number because you put in some initial guess, okay? So initial guess is 1.0 or 1.5, whatever. So it's a fixed number. So how do we guarantee that? So what condition? Yeah, so what condition? What condition on G prime X star so that En go to 0 and N go to infinity in absolute value? So what condition? So you see the last equation, yeah? So the last equation is G prime X star to the power N. So what condition do we want? Yeah, somebody say yes, exactly. So we want this to be less than 1. So if G prime X star less than 1, yeah, in absolute value, then you see that the En we go down to 0, right? And you see that what is our previous example? So if you have X equal E to the X, yeah. So what is G prime? So G is just E to the X. And so G prime is E to the X again, right? And X star is around 0. Well, in this case, then we don't know the correct solution. But you see that when you plot, so suppose you have E to the X, yeah? So E to the X is maybe something like this. E to the 0 is 1. E to the X is something like this, yeah? So you can plot it, yeah? And you can see that the solution is somewhere here, okay? Somewhere, I believe that it's, well, we have to find out what is X star, right? And then we can check what is G prime X star. Yeah, but you can see that it will be bigger than 1. So let me check. So in our case, so let we go to MATLAB and we try to find. So now suppose I plot. So I clear everything. Then I plot. So lin space say 0 to 5, 100, maybe 1,000 points, yeah. Then I plot X plot E to the X and X plot X plot it on. Okay, so Oh, maybe it's too big, so maybe this one is only say 3. Yeah. Well, the problem is it doesn't have solution. So the problem is when I plot it. So this one is e to the x, yeah? And this one is y equal x. So it doesn't have solution. So in this case, we cannot check G prime less than or bigger than 1 in this case because it doesn't have solution. So the methods doesn't have a solution in this case. Okay, but anyway, in general, you know, we want, if you want a conversion, then you want G prime less than 1. Okay, G prime at x star. X star is the fixed point. Yeah, and then you can have a conversion of the fixed point iteration. Okay, so otherwise then the errors will blow up. And so this one is another example of fixed point iteration. So you have x here, you have g of x here, and then g prime is this equation. And then, you know, I mean, after a few iterations, you can see that errors is going down, right? And this one shows that en over en minus 1 is a constant. Okay, so roughly it's a G prime x star. Yeah. So